Hello students, in this video we'll discuss the Euler Mascheroni constant. Let's consider the numbers hm, which are 1 plus 1/2 plus 1/3 plus all the way down to 1 over m. These numbers are the harmonic numbers. Okay, we know harmonic numbers increase without bound. These numbers tend to infinity as m tends to infinity. So what we're going to do is we're going to temper them by considering a sequence. Define am, which is going to be these numbers hm minus the natural log of m. Okay? Good? And so now what I'm going to do is I'm going to say since 1 over x is decreasing for x greater than 0, we have for any k greater than or equal to 2, if we look at the integral from k minus 1 to k of dx over x, this is going to be no more than the value of this function at the endpoint, since it's an interval of length 1, k minus 1, and that inequality is actually going to be a strict inequality, okay? And strictly bigger than 1 over k. And so what I can do now is I can sum this up. K goes from 2 to n. So sum this inequality, this can be summed from k equals 2 all the way up to m. If we sum k goes from 2 up to m over here, I'm going to get the mth harmonic number minus 1. So it's going to be hm minus 1, strictly less than, if I go from 2 up to m, that's going to be the integral from 1 up to m. So that's just going to be the natural log of m, because the antiderivative of this is natural log of x. And if I go from 2 to m, this is going to be a 1 plus 1/2 all the way up to 1 over m minus 1. So it's going to be the m minus first harmonic number. Now let me subtract hm from this inequality. If I subtract hm from this inequality, what's going to happen? We're going to have negative 1 is less than natural log of m minus hm. And then hm minus 1 minus hm, the only thing that's left over is just an hm with a negative sign. So it's going to be less than negative 1 over m. Now, of course, this thing inside the inequality over here is exactly just the negative of am. So this tells me over here that am, by flipping the signs, is between 1 over m and 1. So my sequence am is a bounded sequence. So the sequence m goes from 1 to infinity, is bounded. That's great. Now I need some sort of monotonicity to show that it converges. So let's do that next. So let me consider. Let's consider am minus 1, m plus 1 minus am. Well, let's see what's going to happen over here. I'm going to have hm plus 1, so I have hm plus 1 minus hm. And then I'm going to have a negative natural log of m plus 1, then a positive natural log of m. And so these first two numbers over here, well, that's just going to be a 1 over m plus 1, 1 over m plus 1. Okay? And then these things over here are going to be plus the natural log of what? Of m over m plus 1 by properties of logarithms. And the final step over here is that this is just equal to 1 over m plus 1, and then plus the natural log of 1 minus 1 over m plus 1. That's going to be the key for us over here. Now I need to recall what the Taylor expansion is. So if we recall, I know that 1 over 1 minus x is equal to the sum k goes from 0 to infinity of x to the k. And therefore we can say, well, if I integrate this expression, I get negative natural log of 1 minus x is equal to what? Is equal to the sum k goes from 1 to infinity of x to the k over k. Because I have a k plus 1 over k plus 1, I just shift the index and get this result over here. So therefore this, this can be expanded over here. And so our expression over here can be expanded. And so this expression over here is equal to what? Is equal to 1 over m plus 1. And then this is a positive natural log. So if I change that positive, I get a negative over here. So I have negative all these series over here. So I have negative the sum k goes from 1 to infinity of 1 over k, and then x is 1 over n plus 1, so I'm going to have an n plus 1 to the k. If I plug in k equals 1, what happens if I plug in k equals 1? This is a 1, this is an n plus 1 to the 1 power, so that's going to cancel out with the first term over here, and that turns into a 2. And so this difference over here is just negative. The sum k goes from 2 to infinity of 1 over k and then m plus 1 to the power k. And so therefore, this sequence over here is less than 0. So am plus 1 minus am is less than 0. And that shows that the sequence is decreasing. So am is a decreasing sequence. So I have a sequence which is decreasing and bounded. And so by the monotone convergence theorem, this implies that am converges to some number, and what the number that this number converges to is obviously between 0. The number that converges is obviously between 0 and 1 is this number gamma, and this number gamma is called the Euler Mascheroni constant. Okay? And the remarkable thing about this Euler Mascheroni constant is, as of the making of this video, it's still unknown if this is rational or irrational. So the question, if gamma, this Euler Mascheroni constant, is rational or is gamma irrational, is unknown. And to this date, it's still unknown. So there's still one of the greater mysteries in mathematics is the irrationality or the rationality of this constant, this Euler Mascheroni constant. It's not even known if this number is transcendental or other properties of this. Many other number theoretic properties of this are not known. One really neat thing is from what we recall with the gamma functions from further videos. It turns out that this gamma is negative the gamma function prime at 1. So there's all sorts of interesting spots that this Euler Mascheroni constant comes up in mathematics, and this proves that the Euler Mascheroni constant arrives from a limit of this sequence that is harmonic numbers minus a logarithm. Thank you very much.